Did everyone just get the weird voice? Cool. All right. Thank you so much for coming to my TED Talk. I'm going to tell you about what I've been doing for a little while. So I'm going to share screen. Desktop one. Let's go desktop one. Where is this thing? Cool. So today I want to do, I don't think we're going to get to all of this, but I've been working on this for a little while. And what I want to answer today is like the question of like, how I can't advance with my keyboard. Oh, that's very frustrating. Hold on, navigator. Do I have to do this? Oh, that's irritating. I can't just. Oh, now you're just gonna see everything. Okay. Well, the question is, what have you been doing, Brendan?
Can't you do it if you don't you have to push the play button?
Maybe,
Yeah.
but I don't want to push the play button. I don't want it to go full screen. It's irritating. I don't know. We're gonna live in this world. Also, Teffy, I'm sorry, I didn't have time to use the proper logo. This deck is just a hot mess. So you just have to live with it. One day we'll get it together. So what have you been doing? I've been building a file system for IPFS for the last, I don't know, 6 months at this point. And so you might be asking, like, is an IPFS already a file system, right? And so the short answer is yes. The file system part of IPFS is, we're gonna have to get more specific today. It's called UnixFS. And so UnixFS is files and folders plus content addressing. We're gonna get a little specific with some terms here. Please stop me and ask clarifying questions if you need anything. It's generally blocks of, or just like directed acyclic graph or a DAG of data that's encoded as protocol buffers. Chris, you've been interacting with protocol buffers a little more lately. UnixFS data is actually encoded in the blocks as protocol buffer data. Whenever you see the QM hashes, this is generally UnixFS data. The interesting thing about IPFS is, it as a block store, it takes those blocks, it stores them, and then it becomes networked. You can move those around really easily because it's content address. You can store files of any size on UnixFS as long as your hard drive's big enough. So 100 gigabyte movies, sure, knock yourself out, that'd be great. To give you a feel for what UnixFS looks like under the hood, it's an abstraction layer. It takes files and folders, which I've illustrated on the left. Hopefully this is like visible to you. It's kind of light. And so and then it turns them into, it breaks all of those files and folders into blocks and represents those locally. And the fun thing about this is it's an abstraction, right? A file system is an abstraction over a storage layer. And when we say words like directed acyclic graph, that can be really, a DAG can be like a really fancy term, but when I say files and folders to you, that's a much easier thing for most people to get their heads around. And so there is a major element of human computer interaction here, where a file system really helps define a great way to abstract over the way that data is stored on a computer. And so in this case, in IPFS, we're turning things into blocks. And this diagram sort of illustrates how that relationship looks in UnixFS. And so in this case, we have a folder A, a file B, another file C, and inside of this folder A, we have a folder D, and folder D contains a file E. On the right side, what IPFS does for us under the hood is it takes these things and it breaks them up and stores them as immutable stuff. And so we would have a UnixFS block representing a folder A, and then these arrows are links to child items, right? And so, we're going to introduce the word nodes for this. And so this is common across most file system implementations. You would call all of these things nodes. So files, folders, nodes. Inside of IPFS, because blocks are actually inside of a file system, generally there's a one-to-one relationship between a file and a node. And so a B file will just be stored as a single stream of bytes on disk, and that's the relationship. Inside of IPFS, that's not the case. We would take a file like B, and depending on how big it is, we would break it up into blocks like this. And so when we say the root hash, we're talking about the block here at the very top of the graph. And then if this file was 3 blocks, these two things would just be full of binary data. And what UnixFS defines is a method for a canonical method for reading this back into a file B. And so we can say, cool, when the user says, give me file B inside of directory A, we know how to path into that. Yeah, IPFS goes and grabs these blocks and streams them back so that the files of bytes look like a file, or the stream of bytes looks like a file. And so this is the sort of translation layer that UnixFS is doing. So far, does that make sense? What's worth noting here as well, not all layouts of blocks look like this. This is what's called a balanced layout of a DAG, where in file E, we have a larger file here that has a balanced tree of blocks. We can also have something called a trickle DAG, which is just much closer to a linked list, where we have the header block links to one block, which links to another, which links to another. But you get the same effect. And so this and what it can optimize for are different use cases. And so a linked list style or a trickle DAG can be really good for movies, where you really just want to stream of single blocks, and you don't want to have blocks that have lots of linked data in the top. And so it can really help different use cases. And so we lay DAGs out differently depending on how they need to look. But the thing that's great about UnixFS is it allows us to think as programmers and as humans in files and folders, and IPFS manages this nightmare of lines and arrows and boxes that make it into immutable data. And so query is on UnixFS today. So this is what we use at the very bottom of our stack to create query data sets. So all query data sets right now are stored on UnixFS, and they're stored in a very specific directory structure. So a data set is always a directory at the top, and then there's always a file inside of that directory that matches our component layout. So we have a dataset.json, we have a body.csv, we have structure.json. And so inside of that, we have the dataset.json file is the most interesting one, where it's a JSON blob, and each of its values is not actually the component, it's a string of the hash that we would go fetch. And query, the software up in application space, reads that dataset.json file when it's coming from UnixFS and goes, I need to go find this file that begins with this hash to recombine everything inside of the data set to make it into the thing that reads back in query the tool. Query is actually kind of old. It's been around for a couple of years now. And in the interceding time since query came out, a lot of new tools that have been built on top of IPFS use a technology called IPLD, which is Interplanetary Linked Data. And IPLD, you can almost think about as a more raw API for building the DAG on the right. It gives you direct access to, I want to create this block and it's going to have these lists, and it's going to give me tools to lay out my data however I want. It's much more fine-grained, and it's much more sort of it quite literally removes the file system abstraction and allows you to talk directly to block shapes and whatnot. Usually IPLD, so where in UnixFS we're using protocol buffers as the actual serialization format. In IPLD, we usually use CBOR, which is concise binary object representation. Whenever you see CBOR, you can really just kind of think JSON, just better for binary, which is basically what's going on under the hood. CBOR and JSON, or CBOR is supposed to be a very binary friendly format of JSON, front variant of JSON. There's a really important limiter on IPLD, the max block size. We can get into why there is a max block size, but basically there is a type of attack you can run where you ask for blocks and then don't actually fetch them. So we want to actually keep blocks under a certain size. And so IPLD data, generally, there are people in the wild who cheat on this, but generally hovers around a megabyte per block, which creates for us some interesting constraints, right? In our world, we're actually, and we have made numerous efforts over the years to convert query to IPLD. But we have this fundamental problem. Query dataset bodies are large files. So we need files. We need to have streams of bytes. Our CSV files can get into the tens of gigs very easily. And that means that this 1 block limit or 1 megabyte block limit is just problematic. And so UnixFS solves that problem for us of having large files. But on the other hand, query is a data catalog. It's literally a giant linked data thing, right? Arguably, the huge advantage of the linked data platform is you're encoding blocks of JSON that are much easier for other people to read and understand. It's much easier to write software around. And so you can think of all of our components, structure, body, meta, schema, all of our components really would be better expressed as linked data blocks, because almost all of them sit underneath a megabyte. So far, so good. But this is kind of the fundamental problem we've been running into. We also have a list of things that we want that don't exist in either of these implementations. We want encryption. I'm going to argue to you today that we want versioning down at the file system layer, and we want merge semantics. These are things that nothing inside of the file system layer is providing us right now. And I'm going to argue to you today that we should tackle all of that I just talked about with a file system implementations, because file systems are a really good abstraction. They help us think, they help separate what is application space from files and folder space. And I think specifically in IPFS land, we're already screwing with the definition of a file system, right? Like if you say that like what happens when you put data on IPFS, it's like actually going into this, we're shredding your data into these blocks and building these DAGs, and then we're networking it, and we're saying you can ask for any root hash, and we're not giving you back a file name. We're giving you back, hey, your content is now should be referred to as this giant string of letters and numbers. So we're already messing with what a file system is. We have a whole bunch of things that we need to build. And over the years, when you look at the sort of thickness of query stack of how much work we've had to do on top of a file system, having better primitives down in the file system layer will allow query's code base itself to be thinner. And so I've been working on tackling a lot of the principal challenges that we have in terms of our own application at the file system layer in an effort to say, hey, can we make this a little cleaner? And can we make the whole query code base a lot thinner by doing a lot more down with the file system? So far, so good. Did I just duplicate that slide? Oh yeah, I already made this. So let's try it. The other thing is just a lot of these features, particularly these, are general utility, right? Encryption, people, like if you're using a Mac computer right now, there's a very real chance that your hard drive is just encrypted at rest, right? Because that is just a flag you turn on. So encryption is just a general utility thing that many people need. Versioning is a general utility thing that many people need. Google Docs has versioning built into it. It's just like a natural bit. And then merge semantics, the capacity to take one file system and another file system and combine them, that's a thing that a lot of people need. And so why would we build this into queries tooling when we could build it into something lower and collaborate our way out of some of these problems? And so that's what brings me to WNFS. And so WNFS is the WebNative file system. While researching this problem, I was like, cool, I started maybe a year ago thinking about, okay, how am I gonna actually do encrypted data? How are we gonna start doing the work around encrypted data? Did some searching around and found the folks at Fission and found their WebNative file system as part of my research. There's a couple other projects that were floating around at the time. The Textile folks had some really great stuff around private things. There's a project called PureGOS, which does encrypted file systems without IPFS. The thing that I liked about WNFS was they also tackled versioning, and they built it on top of IPFS and written it in TypeScript, and we're actually targeting the browser. So WNFS is already out. There's a version 1 of this out. Today we're talking about version 2, which is a spec written from lessons learned from V1. It's a work in progress. There's Philip at Fission is working on the TypeScript implementation. Expeed or Brooke is the one sort of quarterbacking and authoring a lot of the spec of what WNFS v2 is. And then we're working on the Go implementation. And the big upside to collaborating here is like, this is like, we're benefiting from a lot of deep technical research that, quite frankly, I'm having spent 6 months writing just the implementation. We did not have the bandwidth to do what we wanted to do at Query in this amount of time. Our goal as a company is to figure out how to get both automation and encrypted data to land in Q1 of 2022. And so the only way that we were going to actually get both of those things pulled off is if we went and found a collaborator. And I think in working with Fission, it has been one of the most productive collaborations I've had in a long time. I find Brooke and Philip to be phenomenal people to work with. They're super amenable to a lot of these changes, and it's been really productive. If you want to see any of that conversation, it's all been happening in the opening. It is on the, the Fission WebNative FS. Oh my gosh, as my computer chokes. but like, just to give you a feel, this is how deep some of these conversations have gone. This is Philip's response to me on how spiral ratchet merging should work. Talking about proxy re-encryption here, celebrating merge semantics, working on different hashing algorithms, like just lots and lots and lots of deep research on how we can make this the best thing possible for a number of folks. And so it's nice to see open source working the right way. And this really feels like open source working the right way. So with that, I'm quick overview of these features. All this stuff is built into WNFS. All files in WNFS are versioned. The way we do that is in that diagram that I mentioned. Each file in WNFS has something called a header block, and that header block includes metadata like, hey, what is this? Is it a file? Is it a folder? How big is it? And then most importantly, what was the last version of it, or versions if that block was produced by a merge commit, which we can talk about in a second. It is encrypted. There are both public and private versions of it, and they operate the same. So all of the encryption semantics are almost all, with the exception of you have to remember to hold on to the key if you want to actually get the data back, are exactly the same. And so the nice thing about this system is we get encryption and versioning all at the base. And on top of that, this is really where the Fission team has worked out a lot of the hard problem. The file system itself is built as a crypt tree of symmetric keys, which means that if you think about a folder having other folders inside of it, each element gets a unique encryption key that advances every time you change the version, which gives you backward secrecy. So you can actually share a specific subfolder at a specific point in time, and that user will not know that they are inside of this child directory, and they will not know that there's a history to that conversation that you don't want to reveal to them. If you want to reveal the history to them, you just give them a key, and then they can go backwards in time as far as you want. You also can share any subdirectory, and that will look like the root directory to them. They won't actually know any of the directory structure. On top of that, encrypted at rest, the directory structure is not visible. You can't actually tell how the files and folders are organized unless you have a decryption key. So this, just real on the real, is the hill that we would not have made it over on our own. The Fission team really worked hard to figure out a lot of these problems. There are some techniques in here that we won't be able to cover today, but are really exciting and really interesting. And I really hope that we get some time to do some deep dives on how a lot of this works, because there's a couple of novel constructions, and then there's a whole bunch of really great uses of tricks like Bloom filters and hash array map tries, and just lots of really nice stuff. Those are the biggies. And then it also includes merge semantics. This WNFS v2 comes up with a spec for how to combine any two arbitrary file systems. Ideally, in the current implementation, I only allow file systems that have a common history to be combined, but this gives us a mechanism for a query. This is the foundation of collaboration, right? This means that you can take a file system or a version dataset tool, fork it, start working on it, and then we actually have a hope for combining those two things back later and getting merge semantics back. The exciting part here, and the very challenging part, is this works on encrypted data. We can actually do all of this we can do merging with history on encrypted file systems, which is really hard. And it's really exciting to see some of that come together. The caveat, if you're thinking about merging, often when we hear the word merge, we think about Git style merge, which like actually takes files and combines them line by line and gives us really pretty diffs that allows us to understand how source code should be combined. In this case, we're talking about a whole file merging. So basically, when we merge two file systems together, you are just going to get picking one file or the other. You are not going to take pieces of this metadata.json and pieces of that metadata.json and combine them into something more meaningfully combined. There is a caveat to that I will get into later, but that's the high level. And then for the Go implementation, we are the first ones to land the merge stuff. I've been working on the merging for a little while, but the other bit that I've been working on really hard on the Go implementation is actually having the Go side conform to IOFS, which is, apologies for those of you who are on the product side of this. This is definitely not the first deep dive into something super technical, but in Go 116, the language standard library maintainers landed a IOFS package, which defined an abstraction for file systems. And this WinFS that I've been implementing implements this file system. And just to give you a feel for like what that turns into, I'm going to show you some source code. Is this the right source code? This is the right source code. So because it's just a file system, if we look at the command for copying, oh my gosh, my computer is choking. I'm sorry. 1 second. Hello, computer. Are you all there? Am I lagging like crazy? Okay. It's just a really slow editor. If we look at the command for, come on. This is awful. Sorry. There we go. Copy. So this is what I want to arrive at for programming. Copy a directory into WinFS. Here's what that looks like. We use the IOFS package to create a directory package. We then just copy from that directory into WinFS. This is the command. And so we go, hey, I want to copy from this path to that path using this local file system access. And so for those of us who have lived through the nightmares of writing our FSI implementation, where we're actually trying to map back and forth between the file system and like block data, that changes for us, where we can now just say, hey, cool, this is a data set laid out on a local file system, please just move it in. And we can do that. And that's a one-line sort of like execution, because all of this is being expressed as a thing that in the Go implementation looks like just any other file system. The fact that it's encrypted and versioned and all that stuff is obfuscated under the hood somewhere else. And it makes it a lot easier to work with. So with that, I want to give you a quick demo, just so you can actually see some of this stuff, and we'll talk through some of these concepts. But before we move to the demo, does anyone have any questions from the presentation side of things?
I left a comment in chat, but encryption, great. How do you handle key rotations, or is there any kind of like thought / strategy? Like we lost keys, so we'll need key rotations eventually, somehow, somewhere.
Yeah. So in the file system layer, so it's symmetric key encryption, and it rotates on every single write. So every time you actually add a file or modify any file, you rotate keys. You don't rotate, you create a new key and you encrypt with a new key. And all of the keys themselves are stored inside of the encrypted tree structure. So those header nodes, when we're in secrets, actually what you do is the only key you hang on to is the key for the root. And if you want to give somebody a different root, you give them the key for that folder. But the key for the root allows you to decrypt the header node of the root. And that gives you the key to open all the children. And then once you have the key, and then you just recurse. And so you can open and open and open and open. So we do need to retain the key at the top. And if we lose that, we actually lose access to the entire file system. That's a real thing. But that's how that's handled. And so it does mean you'll see some code when we deep dive into this after the presentation, Asmir, where like every time you actually have any type of mutation operation, you already have to retain the new root hash, right? Because we've changed something, but you also have to retain a new key. For the engineers, I will show you how all of that works in depth when we go. We'll have to do a deep dive on the encryption side of this, but for now, I'll just give you like a quick smattering of what that looks like and hopefully point some of that out as we're going. So I've written today, I'm not going to be showing you like query data specifically. I'm going to instead just talk to you about like WinFS data itself and like what it looks like. So this is just like a demonstration tool. I wouldn't consider this like production, like we need this thing, but it's useful for like demonstrating what a file system looks like. So right now I have a tree inside of WinFS. And so I can type the WinFS tree command. This is my folder. This is my WebNative file system. WinFS uses very similar to Unix, where we have like user and directories and bin directories where the directories actually have special meaning at the top. Inside of classic WinFS, you have a private folder. Everything that you put in the private folder, guess what? Encrypted. Everything you put in the public folder, any guesses? Plain, unencrypted. I'll make this larger for those of you who are leaning in. I apologize. Is that better? Cool. So we can do, so this is just like a private folder with a file named 2, and then a public folder that has 2 Alice and Alice2.txt. Right at the gates for Chris, I can do WNFS-diff. So we know between any 2 versions, it gives you a sort of like Unix style, hey, what changed? And in this case, this is an A for added, the file private 2, and this is the contents that were added. And so if I do touch, or what do I do? Let's look at what's in here. Touch apple.txt. Please don't make fun of the fact that I do not know how to use the command line. No command line skills. I know there's a way to like echo into files, whatever. I don't do it. But I can do WinFS write private apple.txt. And so I'm giving it, I'm actually deciding the path here. So if I wanted to add a subdirectory, I can just say apple private fruits apple.txt. And then I'm going to do apple.txt. So that what this is doing is saying write to this path on WinFS, this file that's on my local file system. Hit enter. We have a new root, WNFS-diff private fruits was added. Does that make sense? And then if we do WNFS-tree, private folder fruits file apple. We can do history, WNFS log private access to public Alice2. So here we have, hey, when was this modified? What was the state? What were its last versions? What's its CIDs? So every single folder, if I do now, WNFS write public Alice2.txt, and then and instead we replace it with Apple contents. Overwrite it, log it, 3 entries. Makes sense so far? Thing to keep in mind, because this is all a DAG under the hood, the history of the root is growing with every single write. And so if we do WNFS log just the root directory, we have a new version for every single mutation. So inside of query, what we'll be doing is we'll be batching all of the writes into one thing and then committing those as a single version change to the root. And so everything gets versioned, including the root directory. On the root directory, you can see there's actually some private elements, and these are the keys that we actually have to retain to be able to decrypt this stuff. But the nice thing about this is like the private and the public is completely transparent. So if I do WNFS cat private 2, that gives me the data, right? And if I do WinFX cat public, whatever, Alice2, it's the same thing, right? And so we get this really nice, it's really easy to, and so we have all the common POSIX stuff too. We can do WinFS stat public Alice2. And this is going to tell us, hey, it's a file. Neat, here's the CID. We also have tools inside. I built some tools for diagnosticing this whole thing because it's hard to get your head around sometimes. And so like, if we want to see what this, I talked about these header blocks, right? So let's actually look at one. So we can WinFS dag get this, and I'm going to pipe this to JQ. WinFS block, my bad. Helps remember your own API. And so this is what a header block looks like. And so what we just said here is WinFS block. So the block thing is just for getting a single block of data. Please don't like turn it into something cool. Just grab me just a block, right? This is what's in this header block. We have the info, which includes all of the stuff that you would see in a POSIX or style file system. So the time of creation, file mode, modified time, size of the file, which is totally buggy because I haven't finished it, my bad. The type of the file, which is an enumeration of different types. There are 2 here. I'm proposing a third. We'll get to that proposal. The version of the actual file system itself, so that if we need to upgrade or change the spec in any way, we have a mechanism for dealing with that. This is going away, but if it was a merge commit, it would be here. We're switching to an array of CIDs for the previous instead of having a merge field itself. All files inside of WinFS include metadata. And so you can actually attach metadata sections to this. That is going to come in really crucially for query. in a bit in a way that we'll talk about, maybe not today. And then we have this link called userland, and then userland is the actual content, the actual data itself. So this is how we're doing history, right? And so you can imagine for query, imagine building query on this foundation, where you now have native access to, I can say, hey, give me the history of just the meta for this thing across all time. And by the way, make it encrypted and stuff. And then the last trick for this, I have to actually, it got so irritating to do this that I ended up writing a script for it. So I'm going to execute it and then I'll talk you through it. We can actually create merges. And so we can actually, this is going to spin up two different file systems. I haven't written the network implementation of this, so this is going to just merge two directories locally. And what's fun here is this is using that same trick where inside of the command line tool, we're just mounting two different file systems and making them talk to each other to actually perform the merge. But in this case, we're creating an Alice file system, making directory Alice. We're adding a file called private to private Alice to hers. Then we're copying Alice's repository completely and renaming it to Bob. And then we're going to modify Alice's file system. So now Alice has a new file. And so now Alice's tree looks like this, where she has public Alice and private Alice and hello. Then we switch over to Bob and we modify something else. And so what's important here about this is now divergent trees. So we have a situation where Alice and Bob have both made edits that are no longer in sync with each other at all, right? The easy merge is strictly ahead where like, hey, you know, Chris made some changes, Brendan didn't change anything. And then so Brendan just takes Chris's changes. But when you have divergent commits, that's where things get interesting. But here we go, we switch back to Alice and we just do WNFS merge and then we give the directory to Bob. And in here we see that the public directories are actually in sync. And so there's not much to do there, but on the private side, we had to do a merge commit. And so down at the file system layer, we now have encryption, versioning, and the capacity to take any two versioned things, which might be data sets in our case, smack them back together. So far, so good. Cool. That's what I've been working on for 6 months. Any questions off the top? There's one last thing I want to talk about, but I want to make sure that we leave some space. Dustin.
For merging, I'm assuming that it won't handle conflicts or auto merge, or is there some sort of way to like combine files that are both modified? Like, is that also just kind of undefined? Or, yeah, what's going on there?
Yeah, and so there's a baked in merge semantic right now of just picking the one with the longer history. And then if they both have the same length of history, you just sort the CIDs alphabetically and go with that. Is that the right way to do it? No. Does it work? Yes. The long-term plan is to make it pluggable. And so we can actually put in our own merge semantics and say, hey, given two paths that are conflicting, provide a function that tells you how to merge those and produce the resulting CID. That's not going to be super hard. Well, it'll be hard, but we have a plan. It wouldn't be the right.
Is it easy to detect when that bad default happens? I guess
Yes.
that's important. Okay.
Exactly. Yeah, you know exactly which two files have conflicted, and you have all the information you need to know how to line those up. And so that function is the arguments to that function will be well provided and will not be confusing. So it'll automatically handle situations where someone just added a file. So like in our universe where someone adds components that didn't exist before, those will just go in, or where somebody modifies components that are unmodified in another place, that will just automatically take the latest changes.
Can we detect renames or moves?
No, not at all. Next question. Chris, you're muted.
Sorry, you were showing the folder structure or the directory structure that has private and public. So if in query world, would dataset.json just live underneath one of those
under
two?
one of those?
Yeah.
So I've written it out to be linkable, so we can have just this one's private and have external information know that, so that we don't have to have that private and public base folder if we don't want it.
Okay.
The WNFS, that is like, yeah, so we don't have to have that. There's an argument that we may want it. We've talked to some users who want to have data sets, like particularly in the gov space where you have a bunch of private stuff that you don't want the public seeing, and then public releases of data sets, that's a great candidate for just having private and public folders at the root. But that's a design decision that we get to make up in application space, and we don't have to necessarily be limited by the folder structure itself.
Okay. And then this, I assume, is lower in the stack than any of the like query namespacing stuff that we.
Yes.
Okay, so we don't, that would
Much lower.
be affected at all.
No. Yeah, we would, all of our namespacing would be pointing to hashes. So like the way that this kind of works is the same it does in query right now, where you basically say this is a root hash. But that brings me to a really interesting point. Having this thicker system, fundamentally the biggest lesson that you'll learn when you spend long enough working with IPFS is the way you lay out the blocks is everything. So we've been talking a little bit about how if I share a screen again and we go back to this block get. What did I do wrong? Oh yeah, test, is that it? Cool. We've built a technology called Logbook. Why does Logbook exist? Its main reason is to be, the reason we started it was to be able to very quickly transmit between two peers versions that we don't have. And that we don't want to send, right? So like query data sets can get really large. When you say query pull this data set, we just want to give you the latest version, and we want to tell you about all these other versions that exist, but you don't have locally, right? And so we have Logbook for synchronizing, saying, hey, this is a lightweight way to talk about the history of data sets. This block that we're looking at right now is a header block. We can just send the header blocks. So the header blocks are, hey, this previous pointer points to another header block that describes what this file was at a point in time. And most importantly, this is the root of the last version, because versioning is now down inside of the file system. I can say, give me the across. Don't give me the down. Just give me root and then the block of the previous, and then the block of the previous, and then the block of the previous. And that looks a lot like Logbook. Not exactly. There are things that we're going to have to keep in Logbook, like who is allowed to act on this in collaboration management, like the actual like set membership stuff on who's allowed to be in the secret club of private data. But the version history part, we can transmit that by just doing a much more selective transmission of what DAG data we send over. Because as you saw, you can do WNFS log. I can show you the log of this. There's no guarantee that says I have all of the blocks underneath this DAG. And so we can do the local remote selective fetching thing entirely inside of the file system. And so this alleviates a whole responsibility that that Logbook has. And we can now have Logbook just focus on who's the collaborators, who's allowed to edit this, who's not allowed to edit this. And that can be just that technology's responsibility. Does that make sense? And the only reason we can do that is because of the way that the DAGs are laid out.
Cool. How soon? How soon do we get it?
So this brings me to the little last point. So I started working on the API for query and figuring out how to actually started doing the work of sewing. For us, the big monstrous package in this conversation is DSFS, data sets on a file system, which after the first tranche of work on this, I actually ported all of our stuff over to one of the APIs that I wrote to make this thing possible. And then I spent 3 months iterating on how to make all this stuff fit together and arrived at a better API. But there is a problem. Back to share screen. We talked at the beginning about, hey, the DAGs look like this, right? And lots of people are using this new fancy thing called IPLD. And it would be better if query data was actually encoded, query structural data was actually encoded natively in this CBOR format. that make sense so far? The reason for this, there's a couple of reasons for this. Some of the sideline benefits are that like, then tools can natively parse and traverse query data. And so the linked data that query is producing is now available to the rest of the DWeb. It's just like a nice citizen of the DWeb side of things. The other huge advantage is the reason that people write IPLD is they get this lower level access to the actual block arrangement API. And query actually needs that. It uses a lot of tricks like that. So remember we mentioned at the top that query dataset.json files right now, as they exist, are written down with strings that reference to hashes. The problem with that is they're just strings. It's not anything that the actual DAG structure is aware of. And so what we would really like to have is an API that looks a lot like a file system, but also natively speaks something around structured data that allows us to give, ideally, something like our dataset.json component. Say, hey, store this as a file, but this file contains links to other files in it. And that's where traditional file systems don't have much for us here. Like there's a concept called a symlink, but that's not the same as what we're talking about here. And so I have not even proposed this to the Fission team yet. This is very new. I've been working on this for like a week, but I am going to propose a third type of file called a linked data file that maps one-to-one to an IPLD block. It has both file and directory properties, and it's aimed at application developers. The main people for this third type of file are people who work in files that end in JSON. And so the reason for this is I still believe that there's this central tension that a lot of folks suffer with. We are not the only people who are caught between UnixFS and IPLD. A lot of people need both streams and blocks. And this, I think, is a way, so you basically have to make a choice. You either choose to write query on top of the blocks API, the IPLD stuff, and then you're gonna have a nightmarish time dealing with the actual like file construction side of things. And they just aren't gonna play nice together. Or you try and drag some abstraction up into the file system to make it possible for that interface to write linked data and read linked data. So I'm going to propose this. I don't know if this is going to survive. I'm going to openly state right now, this may not land the way it is, but I want to demonstrate to you what it looks like. If I do WNFS lists, let's see, actually, sorry, first there's also diagnostic data on all of this. So I can do query logging is going to be info so that this is a little less verbose. And then let's make this a little bigger. But actually, let's do tree. So we can blow this away and do query to commit. This isn't real. This is just like an API that I've been playing with to sort of make this all work together. But what that has done is this is creating these linked data files that I just mentioned. So if I do, and now I'm going to use WinFS tools to inspect what that query binary just created. But if I do WinFS tree, it's just made a file called meta inside of a private directory. And if I do WinFS stat private meta, you'll see the type here is a data file. And if we do WinFS block get this and pipe it to JQ, it's going to look like garbage for a couple of reasons. First, it's encrypted. And so this is the info section, but that's encrypted data, so you don't get to see what it is. The value is actually inline directly into the block. And so this is one of the first things to keep in mind, that if this is a meta component, so if I do WinFS cat private meta, we're going to get JSON. And so the reason for that is I'm calling JSON the diagnostic output of a linked data file because it's just the most rational thing for a file system to produce for you. The fact that this would spit out CBOR data is insane. But if I do WinFS block get and I do raw, and I give you, so the raw flag is going to say, please don't translate this for me. Now, of course, it doesn't work. All right, I can't pipe that to JQ because it's not JQ. Hey, So here's the raw CBOR data encoded as hex. And so this is a CBOR encoded block. This is like literally an IPLD block. But in WinFS land, we register it as a file. The reason it's also a directory is because blocks can contain links. And directories are just a shit ton of links. They happen to be a schema that is links only. And so what this lets us do is we can now mount any IPLD block as a data file inside of this file system. So we can just create links that say, hey, cool, be in here. And you could literally, using the system, linked to the entire Filecoin state tree, and it would show up as a massive directory structure of files and folders that would actually allow you to navigate through them all. But the hard thing to get your brain around with a data file, it is both a file and a folder. It exhibits both behaviors at the same time. If there are no links, then it's a directory with no contents. But if there's any content, it's content. When you try to read from that stream of bytes, it's going to stream to you JSON by default. In application space, we have something different. We have a different API that we can manipulate, which looks like, is this my query too? No, this my query too? Yeah, cool. For the actual programmer API, this is like really who this is targeted at. In the end is us, and being able to actually like reason about how this shit gets laid out in programming sort of like time, right? Is we will do stuff like this. We would do WinFS write private meta, and I'm going to declare a new data file. And the thing that's interesting about data files is they have to be structured data. So I'm just going to literally give the meta component directly to the data file wrapper, and it's going to handle the serialization for me. And so I'm going to say, cool, here's my struct. You figure out how to encode it. It's got to boil down to the basic data types of JSON. But when I ask for it back, so if I do the inst WinFS, I'm going to do read data file or open data file. Actually, I should use the semantics. I'm going to change this to. So open linked data file, LD file, private meta. This will look a lot more like what unmarshalling into binary or deserialization looks like in query. So I would just do ds.meta. And that would just basically say, cool, just populate that data. And so the serialization is happening transparently. We're going directly from CBOR into the meta component. And that's being handled by the file system for us. We're not worrying about what you often see is like inside of query right now, we're taking a stream of bytes, we're decoding it into JSON, and then we're moving it into, we're decoding that JSON into the struct, the meta struct itself. But the file system itself has no awareness of the JSON. By giving it this linked data awareness, we can actually store it as CBOR, which then all of the world of IPFS will like and IPLD will like. It will also collapse this into one block and get us one. It'll ideally avoid in application space. The user can see JSON if they look at it like a file system, but we don't have to pay the JSON tax of deserializing into CBOR, from CBOR to JSON, and then to our file system, then to our runtime structure. It's a lot, but to answer your question, how soon, Chris? I have to go take that, propose that. If they're into that approach, I mentioned that somewhere in this conversation that the fact that every file can include metadata, I'm going to propose that the metadata component be a metadata field inside of these headers be a linked data file, which we will then use to lay out all of the components about a query data set that are in fact metadata, which is structure, meta, everything that isn't the body, basically. Stick it up there and what that will allow is we can now have file systems that can natively speak data portal type shit, where you have it's a lot easier to build these things out in a way that other people are doing very similar patterns, where you're like structuring data, storing it on file systems, and then annotating that data with metadata. And so for us, we've always had this problem where these components are actually metadata, but we don't have a file system that defines them as such. And so we can have the metadata component, the metadata field in a WinFS header block will be the dataset.json linked data file. And then all of the things will be childed under that. And all of those are at the file system level about the body, which makes this all much more harmonious. And so when you go to read this thing, The like CSV export is go get me that thing and ignore the metadata. The thing that query is going to display is, hey, there's this file, and I now have all of this rich cataloging information that I can access to display properly and read properly. So I think this is very doable inside of Q1 2022. I think it's really reasonable to say, like, we have the API figured out. I have the cursory sort of like pass of how does this all work. And so I think that inside of 60 days, 70 days, we'll be looking at a cursory version of this that covers a lot of this new ground. Whether that's productionalized, you know, that's really up to be debated. But hopefully that answers your question. Does anyone have any questions on the linked data concept? It's easily the most contentious proposal. Dustin.
So does this mean like things like structure, for example, can point to other stuff directly in IPFS land? And if so, like, does this require explicit like opting in, or can this be done more automatically because we have like knowledge of how things are structured to begin with?
So it is opt-in the sense that you have to include the notion of a link in your data structure.
Maybe opt-in is not the right way to put it. It's like, does anything have to be modified from how things are being done now, or will this kind of work like mostly transparently?
Yeah. So for us, because we've already been built on this, it'll basically be transparent because we're already doing all this dereferencing under the hood. We're just going to change some types from string to cid.cid, which is the content identifier data type. And that's it. We're done. And the huge advantage there is like, there's a world where we have the schema section inside of structure, right? If multiple data sets use the same schema, we get that trick where we can just say, cool, the schema is now a link and it's a data file inside. And so we can lay that out the way we want to lay it out. And that will allow us to dive down into the block layer from a file system abstraction.
If when this change happens, how much is backwards compatibility an issue with keeping the current format of bytes?
So I've designed a mechanism to forward propagate this stuff. Basically, if the userland content points at a UnixFS hash, it'll just interpret it as UnixFS data. So then you can imagine how we do not have to backwards propagate all of the stuff. As long as we keep the code around to read UnixFS query stuff, we're good. We can, if we want, rewrite whole histories to make it all clean and work with the new system. But the new system is able to point at the old kind of file and folder structure.
That was the thing I most wanted. So, okay.
Yeah. So backwards compatible in the sense that it will recognize it and make it part of it. Obviously, you can kind of get away with like versioning that stuff, but why would you want to? So like basically, as soon as you write a new version onto the new system, it'll just transparently flip to this new way of laying stuff out. Thoughts? So there's some downsides, and we should all be asking why we shouldn't do this. So some of the downsides, UnixFS is supported natively inside of IPFS. And so the gateways, if you go to ipfs.io/the hash, it just looks like files and folders. We're going to lose that, right? We're no longer going to be able to sort of like just show somebody really easy peasy. For us, we happen to have this thing called query.cloud that like renders our data sets a lot nicer. So we don't really need it. The gateway trick, I'm not wildly worried about. This is the other massive sort of challenge here is that header block thing kind of screws with pathing inside of IPFS the way it works. Because if you can imagine the way the UnixFS works, you go directory, which usually starts with a hash, and then we do like /folder/file, right? And that's really easy and transparent because there's a one-to-one relationship between the links. There's a way that it's sort of baked into the UnixFS protocol that sort of works properly. That we have a system for that. Obviously, I was showing you it during the demo the whole time where we're just pathing and it's naturally happening, but it doesn't actually match one-to-one to what the link structure inside of IPLD is because of the header blocks. So what you actually see under the hood is like the root is a link to a header, and then you have to type /userland, and that actually leads you to the data, right? Which is a little bit confusing because when we're typing, like I'm just like saying like, hey, give me public/meta. That's the meta file. But under the hood, what's happening is we're going public is this CID, load that header block, open userland, and then there should be inside of that a link called meta, open that CID, and then open the link called userland. And that's the file that the user wants to see, which is confusing as shit, but it's it's the price you pay to get versioning and to get all of this like rich metadata inside of your file system. So active thoughts to work on there. Chris has got a question.
Did I just hear you say the user won't see that? They'll just type in.
They won't. Yeah.
Okay, so confusing as shit for the engineers, but no.
It might show up if you're talking to raw data, like if you actually are accessing this on the gateway, but we would ideally, we would just be shipping software that says, hey, if you want to talk to WNFS data, use a gateway that speaks WNFS. And so you won't have this problem. The last one, and this is again for the engineers, this thing is a fucking nightmare for pinning, like actually retaining data, like figuring out how do I pin this structure? There's a lot of reasons for that, but the biggest one is there are some points where we actually have to encrypt links. And as soon as you pick a link and you put it inside of an encrypted thing, you have the same problem we have with dataset.json and stringified CIDs. So lots of active research to go into that. The way that the Fission teams handle this is they literally just turn off garbage collection. So like every block header added to their stuff, they just hang on to forever, which is not great, but we're doing something similar. And so just don't run garbage collection until we figure out the answer to this problem. I think it's going to end with redesigning pinning, but those things we can get to sort of skirt that problem by saying, we're going to have to figure out a design solution. We want to actually implement that solution. We don't need that solution to be implemented to have these tools. And the last is, this is new code. It's got to be made performant. And it's got to be made correct. I've been working really hard on the interfaces, the abstractions, the tests, and like being thorough about all of this, but I have not done the performance pass on it. I have not done the the tuning that makes this truly sing. On the upside, I've been talking to some folks who have some ideas on how we can make this even faster than UnixFS, which I'm very excited to implement. So it's just work here. But the huge benefit is like, we're doing this as a collaboration. This will come with a TypeScript implementation out of the box because there's somebody writing it right now. And that's a huge advantage for our front end crew who may want to be able to just access this stuff directly and work with this block data directly. This comes with the incredible labor of everybody that actually wrote this spec. And so we didn't have to have an in-house research team because the team of Fission did it. So this would have taken at least another year to get to the encryption side of things. And it comes with a whole bunch of things that I personally wasn't even planning as necessary for our initial roadmap, like the capacity to share subdirectories. That's the other thing I should point to. Doing attachments in this world, very simple, really, really, really straightforward, because it's giving us an API to manipulate the tag. So this is where I want to take us. Engineers, I want to do deeper dives with you on this as time comes over, but first I just want to get the high level overview into everybody, including your head, Teffy, because I know this probably is just a lot to take in, but this is the kind of work that we're doing at the low level. And I really invite you to sort of think about this and ask questions, because with this go round, I'd like to have much more literacy around how this whole thing works. Like we're literally taking the entire file system out of IPFS, putting in our own and saying, this is how this is going to work. And so we're going to need more eyes on how that's laid out, how that's structured, more diagnostic tools for people to understand how this stuff is all put together. So I've been putting diagnostic tools in from the get-go. Query engineers, I'd really encourage you to download the WNFS-Go repository, play with it. You saw me do a couple of tricks that I'll put in the README. If you do WNFS_logging equals debug, you will see a lot of debugging information as an environment variable. And then you can just play with it as a file system. But yeah, thank you for coming. This is a lot. Does anyone have any final questions? Cool. Coming soon, private data collaboration. There's a whole other access control side of this that we haven't talked about. We'll save that for another day.
Cool.
Thanks, everybody.
Thank you.
Yes.